This question is asking us to minimize a function of r and h subject to the constraint that r squared times h is 54. And so we have f to be the function we want to minimize, and we create this function g to be equal to the constraint set equal to 0. So it's going to be r squared h minus 54. We create this function capital F that will be f, the little f, minus lambda times g. Also we have the fact that r and h must be positive. We'll see where that comes in later. So the first step is to create this capital F function, and we need to take the partial derivatives of it. There's 3 that we need. There's the partial derivative with respect to r. So from this first term we'll get 4 pi r plus 2 pi h, and then from the last term here we'll get minus 2 rh with a lambda on it. That's the r partial. The h partial has nothing from the first term, 2rh from the second term, and then minus r squared lambda from the last term. The third partial is a technicality. The partial with respect to lambda is basically going to be the constraint. When we go to set all these equal to 0, we're going to find that from the first two, our job is to get information relating r and h to each other, and from the last one, it's just going to be that at the same time we want to satisfy the constraint. And so there's many different ways to do it. Some problems have nice tricks about them that make it work, but I wanted to provide you some standard way that helps you through almost every problem, and so that is for you to solve for lambda in each of the first two and set them equal to each other. And so if these guys are equal to 0, we'll move the lambda terms over to the other side. So we'll have 4 pi r plus 2 pi h equal to the lambda 2rh, 2 pi r equal to the lambda r squared, and then our last one is just the fact that r squared h is equal to 54. We're going to solve for lambda in the first two and set them equal to each other. So we're going to divide by 2rh. And we should stop for a second to think, oh, is it possible that we could be dividing by 0? But that would require r or h to be 0, and that wouldn't satisfy the constraint. The constraint is the product of r squared times h being 54. So no worries there. So we have lambda equal to that, which hopefully, or maybe not, it is not totally necessary, but you can factor out a 2 at least from all the terms. And so we'll have 2 pi r plus the pi h all on top of rh. That's what lambda is from the first partial. That's with respect to r there. And the second partial we have with respect to h, moving the r squared over by dividing by r squared. We'd have 2 pi r divided by r squared. Once again, r can't be 0. And then we simplify that by canceling one of the r's from the denominator. So we'll have the fact that lambda is 2 pi over r. And so the structure is then to set these equal to each other. The fact that we'll have the first equal to the second. Our job, our goal out of this is to get a relationship between r and h that we can take into the constraint and make it into a single variable function, and then we can solve it. So on the next slide, we'll take a closer look at that. We have the lambda from the first, the lambda from the second, and we have to simplify this by cross multiplying. We'll have 2 pi r squared plus pi rh equal to 2 pi rh. Cross multiplying and distributing the r, and then set this equal to 0. You don't want to be dividing by anything, so you want to set things equal to 0 and factor out. That's how you solve these types of things. And so subtract over the 2 pi rh, and it combines nicely with the second term here, pi rh. So when you subtract over the 2 pi rh, you end up with minus pi rh. And now we can factor out. We factor out the r that they have in common, they also have a pi in common. We can factor that out too. Factoring out pi r, we're left with 2r minus h. And these are multiplied to be equal to 0, so one of them has to be 0. Either pi r is 0, meaning that r is equal to 0, or 2r minus h is 0, meaning that h is 2r. R equals 0 isn't a possibility. Remember now the constraint is r squared h equals 54. So if r is allowed to be equal to 0, then that wouldn't satisfy the constraint. H equals 2r is what we desire. That's what we wanted to get out of Lagrange, is the fact that h was equal to 2r. Okay, and what we're going to do with that then is to go to the constraint. R squared h is equal to 54. Replace the h with the 2r, and we're looking at 2r cubed is equal to 54. If 2r cubed is equal to 54, then that means that r cubed must be 27, conveniently, perfect cube, and we'll have the fact that r is 3. Knowing that r is 3, we can go backtrack and figure out what h is. H is supposed to be double r, so h is 6. Our job next should be to go evaluate the function. Plug in this 3 and 6 into the function. The function was 2 pi r plus 2 pi r h. That was our function. So plugging into that, we have 18 pi and another 36 pi, so altogether 54 pi. The issue is this is all we're getting out of Lagrange, just one outcome. And so Lagrange is guaranteed, by the way it's set up and the way we derived it, to give us an extreme value. We just don't know, is this extreme maximum, extreme minimum? Is this an absolute max or is this an absolute min? We don't know. And so, here's what we need to do. When only one extreme value comes out of the Lagrange Multiplier Method, it's our job to make an argument as to why this must be an absolute minimum versus a maximum, or vice versa. Here's how you go about that argument. What you do is go to your constraint and find another set of r and h that satisfy that constraint. And take that r and h and plug it into the original function. If that outcome that you get is more than what you got before, then that means that what you got before must be an absolute minimum. If that output that you get is less than what you got before, then that output that you got before must be an absolute maximum. And so it's totally random. Whatever the key choice here, the key thing in the problem is that they said that r and h both had to be greater than 0. So that puts some constraints on us. It helps us to only have positive values of r and h for the choices. And so something like r equals 1 and h equals 54 is a good choice. On the workbook, I think I have a typo here, and I mixed these up, and I made r equal to 54 and h equal to 1. But this is the choice that I was looking for. That satisfied the constraint, and when you plug that into the function, you end up with something higher than 54 pi. You get the 2 pi, and then you get the 108 pi, so you get 110 pi. And so we are in the first case here, where it gave us something higher than our output, 54 pi. That means our output of 54 pi must be an absolute minimum. Okay? And all Lagrange has a kind of structure to it. You might be along the way able to find some tricks, multiply by x, y, and z, and things cancel nicely. Those tricks are only special for those particular problems. And so my recommendation is to stick to the structure of solving for lambda in each and setting those equal to each other. If you have any questions, please comment down below or email me.